Hi class, welcome to the next section, chapter 4.6. Today we're going to talk about implicit differentiation. So implicit differentiation is a direct result from the chain rule. It's really a way for us to differentiate what we call implicit functions. So it's not necessarily a whole new rule like the chain rule or the product rule or quotient rule. And it's not a rule for specific types of functions like cosine and sine or polynomials and exponentials. It's more so another way that we consider functions or categorize functions and how to deal with those type of functions. So before we begin, we have to really just talk about what is an implicit function. Okay, so we really define them into two categories. There's explicit functions and implicit functions. In my pre-calc class, I talk about implicit functions like literally for like 2 seconds in one single video. When we talk about inverse functions, we kind of breezed over that topic here in chapter 1 as well, but we didn't specifically call it an implicit function. So an explicit function is a function where we can write the function as y equals something. Okay, and now you're probably saying, well, duh, Professor Williams, all of our functions are y equals something or f of x equals something, right? But there's certain functions that we cannot categorize as y equals something. Sometimes we have to have a y squared in there, or a y cubed, or a y to the 4th power, or something to that effect. Okay, those functions are called implicit functions because I do not explicitly have a function for y. Okay, so that's why we call it explicit and implicit. So again, an explicit function is y equals some rule. Okay, an implicit function is basically all the functions that we can't write in that form, such as circles, hyperbolas, not parabolas, but rotated parabolas, a lot of the conic sections basically. Okay, so an example is the circle. That's the easiest one to use. We've already talked about the circle, specifically the unit circle in this class, and from your trig you've also learned about the circle. So here, let's say we have a circle of radius r. I cannot isolate y, right? You probably have never asked yourself, how come they never just say y equals the square root of whatever? Okay, and the reason is because it's not technically a function, right? A circle does not satisfy the requirements for a function. It doesn't pass the vertical line test, right? So if I want to talk about y in terms of a function, I actually need to have two functions in order to do so, right? I have to have the positive half, square root of r squared minus x squared if I isolate y. And I have to have the negative form, right? Remember, when you square root something, you get a plus and minus. So I would have a positive function, the top half of the semicircle, and the negative form, which is this bottom half of the semicircle. I cannot write a circle as y equals one function. I have to write it as multiple functions. And that is why the equation of a circle is an implicit function. It is not possible to explicitly write the equation of a circle as y equals something. Okay, a single function, I should say. I have to write it as a combination of two functions. Typically you see this as plus or minus square root r squared minus x squared, right? But that is still two functions, the positive and the negative forms, right? So the equation of a circle is an implicit function. So then we would say to ourselves, well, I should still be able to talk about the rate of change of a circle because a circle technically is changing at all points, right? It's always changing. A circle is never constant. So how do I describe the rate of change of a circle? And that is where we get implicit differentiation. How can I talk about how a circle is changing at a single instance? Now, obviously, its rate of change should pretty much be, it's not constant because if you look at a circle, there's times where the tangent line has a slope of 0. There's times where the tangent line will have an undefined slope, where the tangent line will have a positive slope and a negative slope. So that is changing as well, right? So we should be able to still differentiate it because we can talk about how the circle is changing at any instant. So again, that's where implicit differentiation comes from. So I'm going to talk you through it. Obviously, that's what we're here for. But I want you to kind of think about the last video that we had on the chain rule. And when I talked about using the U, V, W, and R substitutions, and how as we kind of went through and we backtracked, we had to use U and the derivative of the function that our function U was in and then we had to multiply that times u prime. And then we later substituted that for the equation that u was in terms of x. It's really kind of the same idea, right? When I differentiate the equation of a circle, I have to think of it as, well, this is an x. I'm differentiating in terms of x, so here I can just do a regular derivative. Here I would actually have to use the chain rule because y is a function of x. So I have to, it's a function inside of another function, it's y inside of itself, right? So I would have to, or I'm sorry, it's y inside of a square function. So I'd have to use the chain rule here. R is just a constant term, so this would just go to 0. Okay, so let's do an actual example. So as we look through our equation, we say what depends on x and what does not. Well, this depends on x. Y we know is a function of x. In this case, r is not. R is a constant. Okay, so we have to know what are constants, what are functions, and what are variables, right? Okay, so again, the most important is y is a function of x. That's the most important thing you want to do. And so whenever we run across y, we have to use the chain rule, especially if it's in the form of y inside of some other function. Okay. Once we do that, we take all of our derivatives of y's, all of our y primes, and we get them on one side of the equation, and we get everything else on the other side of the equation, and we solve for y prime explicitly. So remember, explicitly means I get that thing on one side and everything else should be on the other side. My y prime should not be squared, should not be to the 4th power, should not be square rooted. I should be able to solve for it so that it is an explicit function and not in an implicit form. Okay. So let's do an example of this. We'll break it down using our function notation and relate that to what we have for y's, right? So we know that for functions, we use f of x, okay? Let's say that our function, whatever it is being cubed. We could say that it's square root of x plus 1, maybe, okay? Some function, it doesn't matter what function. Sine of x, it could be tangent of x. But whatever's happening, I'm cubing it, okay? So I'm taking that function and I'm raising it to the 3rd power. So if I want to find the derivative of this, I have to use the chain rule, right? So I differentiate the outside function, which is it being cubed. So I get 3 times my function, now squared. And I have to multiply this function by the derivative of my function, right? So remember, you differentiate the outside function, keep the inside function the same, and then multiply that times the derivative of the inside function. So that's the chain rule. We know now to relate it to y's instead of f of x's, because you'll never see f of x you'll never see x squared plus f of x squared plus r squared. It'll always be x's and y's. We know that f of x is the same thing as y. Okay, so everywhere I see f of x, I'm now just going to replace it with y. So I'm going to write this as the derivative of y cubed. Okay, so my y cubed is f of x cubed, right? Y is f of x. Okay, y is f of x. So f of x cubed is the same thing as y cubed. So when I take the derivative then, okay, the derivative of f of x cubed is the derivative of y cubed. I'm just making that substitution. So then everywhere I see f of x, I can plug in y, and that's it. Okay, so this is going to give me product rule, or I'm sorry, power rule, right? So 3 will come down, 3 will go to 2, so I'll have 3y squared. And then I have to multiply by the inside function, which is y, so times y prime. So I have 3y squared, okay? But remember, y is not necessarily a variable, it is a function of x. I'm differentiating with respect to x, so I have to use the chain rule and multiply this times the derivative of my inside function, which is y. So I get 3y squared y prime. So that is how I differentiate implicitly an implicit function. So let's do an example. I'll give you guys a second to pause and write this down, but let's go ahead and do an example. Okay. So let's say we want to differentiate dy dx by differentiating y squared equals x squared implicitly. Now, that does not mean you just differentiate this side and say, oh, that's equal to, that's what it is. It's 2y times y prime. I differentiate both sides of the equation when I have an implicit function, because I can have y's on both sides. I can have variables on both sides. So I differentiate the entire equation when I differentiate implicitly. Okay. So this will turn into 2yy times y prime. Okay, the 2 drops down, the 2 goes to 1 for the exponent times inside function y, right? I multiply that times y prime on the outside, and on the right hand side, I differentiate like normal because it's already in its form of x, so it just turns into 2x. Y is a function of x, so I differentiate it like it's a function. So differentiating on both sides, we first take the derivative. So notice I'm not writing dy dx, I'm just taking the derivative of these specific functions, right? Because both sides are not in forms of y yet, or as a single function where y equals something. So I'm just taking the derivative of this and the derivative of this with respect to x. Okay, so since this is already in a form of x, just differentiate. Since this is not in an explicit form of x, I know that y is an equation in x, so I need to differentiate implicitly. That's why we use the chain rule. Okay, so I'm going to get my 2y times y prime. This will go to 2x, and then isolate y prime in order to find my derivative, because dy dx is the same as y prime, right? D over dx is not y prime. So in order to find dy over dx, I isolate my y prime, so I divide both sides by 2y, and I end up with x over y, and that is the derivative of this function. So I differentiated both sides, okay? One like normal, one implicitly. So in total, we call it implicit differentiation because it is an implicit function. And then once I get my y prime, I isolate it because it's going to be possible to have y prime on both sides depending on the equation we have. So we get them all on one side, and now I have an explicit function for the derivative. Okay, so here we're going to find the equation for the tangent lines to the circle that have a slope of 1. So first of all, I need to find the derivative of my unit circle. Okay, so that means that the radius is going to be 1 and not r like we had before. When I differentiate implicitly. So I will have 2x. I know that the derivative of y squared is 2y y prime. And then 1 will disappear and go to 0. Okay. I need this thing to equal 1. That does not mean I just set it equal to 1. The derivative, right, the slope of the tangent line is equal to 1. So I will isolate y prime, and then I can set it equal to 1. So I'm going to subtract my 2x and then divide by 2y. So now I know what the derivative of y is. And this is the equation that gives me the slope for anywhere in the unit circle. So here I need to set this equation to 1. Okay, so I know the derivative is 1. So I'm going to get a set of equations from this. So I'm going to set this equal to 1, and that gives me my original equation, x squared plus y squared equals 1. My x and y has to satisfy that. And I also know that if this is equal to 1, I can just multiply both sides by y, so I have y equals negative x. Okay, so I have my original equation and my derivative equation. So solving this is going to give me 2x squared equals 1. Just in case you're a little fuzzy on how this works, I can just take y and I can substitute my negative x. So then I get x squared plus x squared equals 1, which is 2x squared equals 1. Okay. Solving for x gives me square root of 1/2 or square root 2 over 2. Okay. So what this is telling me that when x equals square root 2 over 2, I have 1 as my slope. Okay. Because first I have to find out the points where this happens, right? So that's why I have the set of equations. Now there's technically 4 points on the unit circle for square root 2 over 2, plus or minus, right? Because it's a circle, so you have the positive and the negative parts. So if you just think about a circle, which of those 4 corners, right? We know that from our experience with trig, that the angle is multiples of pi over 4, right? 45-degree angles. So which of those give me positive slopes? So hopefully you can picture in your mind, and you can say, oh, well, that's when I'm at 135 degrees, right, in quadrant 2, and when I am at 315 degrees in quadrant 4. That's when the tangent line has a positive slope. Okay. Help us visualize what's going on a little bit. This is my points, right? So if I think about when x is Square root of 2, square root of 2 divided by 2. I guess I can just write this as 1/2. Okay, there's 2 points just for that one. Okay, because it's a circle, and we have negative square root, and we'll do the same thing. Okay, oops, let's say x equals. So there's 4 points where this works on my circle. There's only 2 of these points where my tangent line will have a positive slope, and that's at the 135 degrees and at the 315 degrees, right? These other 2 points, I'll have a negative slope, a downward slope. So that's how I know that this works. Notice if we write negative x over y, we won't get an equation because it's explicit. Let's say I went y prime equals negative x over y. We won't grab that either. If I'm looking for points when it equals 1, then that's y equals negative x. Okay, so that also gives you those 2 points of intersection here, right? This is what I had from my system of equations. That was when I simplified 1 equals negative x over y. This was the equation that I got. So this is the points where it works. And notice that it is when x equals positive and when x equals negative, but it's only 2 of those specific points, the 2 that I pointed out, not the other 2 points on the unit circle that satisfy these 2 x lines. Okay, so this is just us looking at what we have so far geometrically, right? Sometimes it's really easy to get lost in the algebra and the calculus if we don't have like a strong sense of visualization for what's happening. So I always try to tell my students to take a second to like draw a picture, draw a graph. That's why we spend so much time graphing things, and why I say, hey, it's important for you to know how to, for instance, graph your polynomials, right? Where the zeros are and where these things are, so you can get an idea of what it looks like rather than having to stay on Desmos the whole time or your calculator. You should be able to just do your math with an idea of where it is that you're working with in space, right? That's really what the goal of, one of the main goals of calculus is to be able to work analytically through your mathematics and through your geometric sense as well. Okay, so let's go back to our lecture. Okay, and again, from my y prime was negative x over y, I got that y equals negative x, put it into my system of equations. I got my 2 points, the plus and minus forms, which I simplified, which was true, but the problem is that it, with relationship to the unit circle, it gives us 4 points, and I really only needed those 2. Okay, so from my own sense of geometry, I know that this is one of the points, right? So this is quadrant 4 because it's positive and negative. So positive on the x, negative on the y. And the other one is when you're negative on the y and, negative on the x and positive on the y, so quadrant 2. So these are the 2 points that we needed. So just to sum up what we have, now I know the points where I have a tangent line with a slope of 1. So I now have a point, actually 2 points, okay, and I know my slope. And I have the equation, this is the equation that I need to use. Okay, this is my original equation. So I'm going to use my equation. Actually, I don't need my equation because I have my x and y. I don't need anything else, actually. Okay, I already plugged in my x values to get the points that I needed. Okay, so I'm going to use my form of a line, y equals mx plus b, with both points. I'll use my first point, plug everything in, right? Y being negative, y equals mx plus b. I can multiply everything times b and simplify, so I would get negative root 2 plus root 2, or negative root 2 equals root 2 plus 2b. When I move this over, I'll get negative 2 root 2 divide by 2 and then get negative root 2. Okay, so or any other way that you like to solve for b, I like to clear denominators. I'm not showing you all that math because we've been doing that for a long time. Right, solving for b at this point should be very easy compared to everything else we've been doing. So that's one of my lines, y equals x minus root 2, because I have my m and my b. So for my second point, I'll have a different line. I'm using negative for x and positive for the y. So when I plug that in, it looks like this. I do the same work to solve for b. And instead of getting the negative root 2, I'll get the positive root 2. Okay. So therefore, my two lines that are tangent to the unit circle that give a slope of 1 are y equals x plus root 2 and y equals x minus root 2. Okay. All right. So next, let's find the derivative of e to the y times sine x equals x plus x times y cubed implicitly. So again, we're going to differentiate with respect to x. So x is our input variable. That means y is an output variable that relies on x. So every time I see y, I'm going to use the chain rule if necessary. Go ahead and pause right now. Now that we've done two examples, go ahead and try to do this yourself and solve for y prime. Okay, so hopefully you tried this on your own. Notice that you have to use the product rule a couple of times. Also, obviously, the chain rule. So let's go ahead and do this together now. So for the first part, I have to use the product rule. So if I differentiate e to the y first, I will have y prime times e to the y from the chain rule. I will multiply that times sine of x. I will add to that e to the y being left alone times cosine of x. Okay. On the other side, x will go into 1. Here I will use the product rule, so I'll differentiate x first. So I'll get 1 times y cubed. Okay. So that's from the 1 plus x, which turns into 1 times y cubed. And I'll add to that x times 3y squared, okay, times y prime. All right. So I'm not done because I have to solve for y prime. Remember, dy over dx is the same as y prime. So my goal is to solve for y prime. So I move everything to one side of the equation sign and anything that has a y prime to the other. So I'm going to subtract ey cosine x, and I'm going to subtract this 3x y squared y prime. Okay, so now I have everything that has a y prime in its term on the left side. Everything else is on the right side. Here I can pull out the common factor of y prime. Okay, and then now to isolate y prime, I divide both sides by this ey sine x minus 3xy squared. Okay, and there you go. That's how we solve for the derivative for an implicit function. Okay, so I believe this is our last example. So here we're going to find the second derivative. So I'm going to do this twice, right? So for the first one, this is just a regular derivative. Here I'll use the product rule. Here I will use the chain rule, and this will go to 0. So I'll get 2x. This will be 1 times y, okay, plus x times y prime. And this will turn into 2y times y squared. And the right-hand side will go to 0. I don't just take the derivative as it is. I can, to be honest with you, I can just say, okay, let me find the second derivative, do the product rule again, and get my second derivatives and all that stuff. But it'll be a lot easier just to isolate my y prime first, and then find my second derivative. Okay, so I'm going to pull out my y prime. I will subtract this and then divide by that. Okay, I get my negative 2x minus y, and I will divide that by x plus 2y. So now when I take the second derivative, this will be y double prime, and then whatever I have here on the right hand side is my derivative. I won't have to solve it, right? So it really is up to you. Do you want to just take your second derivative from here and then isolate your y double primes and then move everything over, or do you want to solve for y prime and then take your second derivative? It really is just a matter of preference at that point. So here we'll use the quotient rule. We differentiate the numerator first, so that'll be a negative 2 minus y prime, okay, multiplied times x plus 2y. I will subtract from that this second form, so I can pull out this negative and just call it positive, okay, or whatever, it doesn't really matter. Multiply times the derivative of this, so that'll be 1 plus 2y prime. Okay, I'll divide that whole thing by x plus 2y squared, square that whole thing. Okay, so from here I want to simplify if possible. Like I said, I'll turn this into a negative. I'll pull out this negative, and maybe I'll just switch the order around. That's typically what I like to do. So here everything is positive. I pull the negative out here. There's a lot of x's and y's and a lot of 2's and 1's. So if we look, this is constant in y prime, constant in 2y prime. So that doesn't help. X and 2 y's, 2 x's and y's. I really don't see any common factors to pull out. So if I want to simplify, I'm going to multiply this through. Okay. So I know you probably say, oh, well, there's an x plus 2y and there's 2 of them here, but I can't cancel unless I have an x plus 2y present on both sides. So I can't cancel anything at this point. I can multiply this through. Okay, so if I multiply this out, I get my 2x, my 4y, my xy prime, and my 2yy prime. On the other side, I'll get my 2x, my 4xy prime, my y, and my 2yy prime. Okay, so now when I add like terms, you can see at least at the end I have 2y prime is the same. I don't have any just y's, but I do have 4, and I have 1 here. I have 2x and 2x, and I have an xy prime and an xy prime. So I have the same thing on both sides. Everything here will simplify. Remember that these are all actually negative, right? So this 2yy prime will cancel. This 2x will cancel. I'll have a negative 3y's, and I will have 3 xy primes over x plus 2y squared. Okay. All right. So the only thing that's left over is my 3y's and my xy primes. Everything else will cancel. Even if I pull out my negative 3 here, I don't have a common thing to simplify. So I'll just pull out my 3. I'll change my order around, right? So I'm pulling out a negative 3 so I can put the prime stuff in front. And that's it. That's my answer. Y double prime is this simplified form, which is a lot easier to look at and use if I have to find whatever it is that would use the second derivative for. It'd be a lot harder to use this than it will to use this. Okay, which we will be doing in this class. We will look at the higher level derivatives in chapter 5. Chapter 5 or chapter 6, I believe.